Hello guys, welcome to the channel. This video is video number 6 of a series called A Young Person's Guide to Calculus, and this is a series that just aims to teach different equations and techniques that cover different areas of calculus. And this video is on differentiating trig functions. And I just want to quickly say before we start that in this video I used knowledge from previous videos in the series. So if there's stuff that comes up on product rule, quotient rule, or first principles and stuff like that that you're not familiar with, please check those videos first because I assume that knowledge going into this video. Cool. So in this video, I'm going to be covering the equation for sine and cosine, um, or what is the identity for differentiating it, the proof, nice proof with first principles, and then derive other trig functions. And that's just because the other trig functions are different combinations of sine and cos, so you can differentiate all of those if you know sine and cos, and then just some practice questions at the end to just get familiar with it. Cool. So diving straight into it. So the two things you kind of just need to know is if you differentiate sine, you get cos, and if you differentiate cos, you get minus sine. And if you look at the graphs, it's kind of intuitive. So just starting off with sine, you can see that the gradient starts off maximum and is still increasing, but the gradient's decreasing. It's still positive, but decreasing until it hits pi over 2, where it's 0, and then starts decreasing um, just like so. And you can see here that cos curve, its maximum is at 0, and then it's positive, but uh, decreases until you hit its sine's turning point, which is when the gradient is 0 here, and then it goes negative, just like so. And you can do a similar thing looking at cos. The gradient starts at 0, and then it goes negative, and it's becoming more and more steep, and then after it crosses cos x equals 0, it starts to round off again until it hits 0. Just like so, you can see it starts at 0, it goes negative, um, and turns around here. This is at pi over 2, and then goes up just like so, and this is pi, which matches up here with the turning point. So that's kind of like an intuitive way of looking at it, just looking at the graphs. The shapes kind of match. In terms of proving it, this is a proof that you guys could even try. If you know how to use first principles, it should be fine. You just need to use these small angle approximations and double angle theorem. Those are extra pieces of knowledge you need to know. But otherwise, it should be well within your reach if you want to try it. But just going through it, if we have y is equal to sine x, then if you differentiate, if you have dy dx is going to be the result of differentiating sine x. And we can write this out in terms of first principles, just like so. And this should be standard, just having a x plus h minus x, like a function of fx plus h minus fx over x plus h minus x. And then we can use double angle formulae to split up sine x plus h, just like so. And also you can cancel out these x's on the denominator to just be left with h. And then what you can do is you can use these small angle approximations because we know h is tending towards 0 to sub out cos h for 1 minus h squared over 2 and to sub out sine h for h, just like so. And then what we can do from here is we can split it up just like so. So I've just taken this h cos x over h out, just singling it out. And then what we can do is we can do some simplifying because if you expand this, this would be sine x minus sine x h squared over 2. And sine x minus sine x is just 0. And then here we have h divided by h, or h cos x over h. So that will then simplify to this. And then you can simplify it one more time to get to this. And then if we apply our limit, h is tending towards 0. So this will be just sine x times 0, which is just 0. And you'll just be left with cos x. And so then you get dy dx is cos x. So that's a nice little proof for sine x. And then similarly for cos x, again, we need to use double angle theorem and our limits, our small angle approximations. We can say that dy dx will be the differentiation of cos x. Apply first principles, which we should be familiar with by now. And what we can then do is use double angle theorem, but with cos, to produce this expression and simplify the denominator again, cancelling the x's out. And then what we can do is apply our small angle approximations again, and we can simplify again. Looks quite similar to the last one. And if we then divide out by h, you're left with this. And now if we apply our limits, this is going to be cos x times by 0, which is just nothing, minus sine x. And so you're just left with dy dx is equal to minus sine x. There you go. That's a nice little proof for sine and cos. Now, the nice thing is that we can construct any of the other trig functions in terms of sine and cos. So that means just knowing these two bits of information, you should be able to differentiate anything else. So I will go through it, and I do have a cheat sheet at the end of all of this, just to have all the information on one slide. But I really do encourage pausing the video and trying to differentiate tan x by yourself before watching me go through it. Cool. So just looking at if we have y is equal to tan x, then we can say y is equal to sine x over cos x. And what we know is we can apply quotient rule here. So we have when we have y is equal to u over v, where u and v are functions, dy dx is u prime v minus v prime u over v squared. And that's great because we can identify u is equal to sine x because that's the numerator, v is equal to cos x, our denominator, and then u prime is cos x, which we just know from our identities up here, and v prime is minus sine x. So then we can then say dy dx is cos x minus sine x over cos squared x. And if we just multiply these brackets out, you're left with this, cos squared x plus sine squared x over cos squared x. And there's a really nice identity, which is that 1's equal to cos squared x plus sine squared x. So you can sub cos squared x plus sine squared x out for 1, just like so. And you're left with 1 over cos squared x, which you can just write as secant squared x. So there you go. So tan x differentiates to secant squared x. Perfect. Now we have secant x. Again, I really do encourage trying it yourself before watching me go through it. Cool. So hopefully you've tried it. So just looking at it, we can write y is equal to 1 over cos x, and then again use the quotient rule where we can say u is equal to 1 and v is equal to cos x because it's another fraction here. And then we can say u prime is equal to 0, v prime is equal to minus sine x, and we can apply it to get that dy dx is equal to 0 times cos x minus sine x times 1 over cos squared x. And if we simplify that, 0 times cos x is just 0, and minus sine x is just sine x. So then you get sine x over cos x, which you can then you can split it up like so, and the way you tend to see it is tan x secant x. So there you go. So if you differentiate a secant x, you get tan x secant x. Cool. Cosecant x is going to be a similar principle of writing it in terms of sine and cos. So again, give it a go if you would like. And if you're with me, here we go. So y is equal to 1 over sine x. And then again, we can use quotient rule, which is saying y is equal to u over v, where u is equal to 1, v is equal to sine x, u prime is equal to 0, and v prime is equal to cos x. And then they will give us this, dy dx is equal to 0 times sine x minus cos x times 1 over sine squared x. And this is nice then, 0 times sine x is just 0, and you're just left with minus cos x over sine squared x, which you can then split up like so to produce minus cot x cosecant x. So cosecant x differentiates to produce minus cot x cosecant x. Here we go, cot x now, almost final one should be. I'm just going to wait a moment just in case you want to try. Cool. So let's give it a go. So we can write cot x in terms of as cos x over sine x. And that is quite handy because we can then use quotient rule again, which is seeming to be our best friend now. And that's because we can say u is equal to cos x, v is equal to sine x, u prime is equal to minus sine x, and v prime is equal to cos x. And so this will produce this, minus sine x, minus cos x over sine squared x. That's a mouthful. Which you can then, if you multiply the brackets out, you get minus sine squared x minus cos squared x over sine squared x. Which we can just write as minus 1 on the numerator, and that's because if you can factor out minus 1, you'll be left with sine squared x plus cos squared x. So that's just minus 1 over sine squared x, which you can then write as minus cosecant squared x. There you go. So that is, so cot x differentiates to minus cosecant squared x. And here's a cheat sheet showing all the results you'll need for trig. And I just have this here to use chain rule when you have fx inside the trig function. So I'm just saying that this cheat sheet applies for when we have x inside. But of course, we want to always be ready. It could be 2x or x squared plus 3 or something. So just being ready for those. And yeah, and that's just also kind of in preparation for some of the practice questions, because for the practice questions, I'll be diving into stuff where x is not the subject. Cool. Here we go. So here's this is practice square. I should say practice questions. I have 5 practice questions here, and I've also just put a quick disclaimer that because of how versatile and mobile trig is, there's so many different ways of producing any result, and I just go through one way, or question 4, I go through 2 different ways of doing it. But you might differentiate differently to the way I do. But feel free to leave a comment if you're really not sure, or try and get to me, email me or something you're working out, and I can check if it's correct myself. Otherwise, just pause the video and give the questions a go. Cool. So diving into it, it's going to say practice square the whole time now, isn't it? Okay, so we have y is equal to cos 3x. So what we can then use is use chain rule, as I said in the cheat sheet. So if we say u is equal to 3x, y is equal to cos u, dy du is equal to 3. Du dx is equal to 3, dy du is equal to minus sine u. And then we apply chain rule, dy du times du dx is equal to minus 3 sine u. And if we know u is equal to 3x, we can say dy dx is equal to minus 3 sine 3x. So you kind of see from this that you can say that if you differentiate cos fx, it's f dash x of minus sine fx. And this is just taking full advantage of chain rule, because all these trig functions are functions. So you can just use chain rule, which hopefully you're quite familiar with. If not, I have a video on it. And that should help for you to tackle some of these questions where x is not the subject. Cool. So looking at question 2, when we're adding terms, and you differentiate them, they're independent, so they don't affect each other. You just treat them as 2 separate terms. It's just only when you're multiplying them that you have to use that they affect each other. And I've just chucked the double angle formula equation in the top right here, just to try and simplify this x squared sine x cos x term, because you can use triple product rule, but it is quite long, or makes your life quite hard, and it's a lot easier to just write it in this form, half x squared sine 2x. And here I've just wrote 1 over cos 5x as secant 5x, just like so. And then just since these 2 terms are independent, we just need to focus on them one at a time. So just focusing on the left-hand side, we can use product rule, where if y is equal to uv, dy dx is u prime v plus v prime u. We can say u is equal to half x squared, v is equal to sine 2x, u prime is equal to x, and v prime is equal to 2 cos 2x. If this feels like a bit of a jump for you because x is not the subject, we have 2x as the subject, you can always use chain rule by saying w is equal to 2x and check it for yourself. But you do get there. Now just focusing on the right-hand side, we can use what we said before, just saying it with chain rule pretty much, which is just saying if I differentiate secant with fx, it'll produce f prime x of secant fx tan fx, and fx in this case is just 5x, and if you differentiate f prime x is just 5. So just subbing these guys into this formula, you get this bad boy, which can simplify just like so, because these 2's and halves can cancel. There you go. So that's question 2 done. Looking at question 3, also you can do some rearranging work to make your life easier. So if we say that cos squared x plus sine squared x is equal to 1, and we divide both the left-hand side and right-hand side by cos squared x, you're left with 1 plus tan squared x is equal to secant squared x. And we have 1 plus tan squared x here. So we can just write this as secant squared x over cot squared x. And then we can work from here, but we can write things out in terms of sine and cos just in case it can simplify. And if you do so, you get 1 over cos squared x divided by sine squared x over cos squared x. And just being careful with your fractions, you can cancel out these cos squared x's to be left with y is equal to 1 over sine squared x. And you can just say y is equal to cosecant squared x, just like so. And then here it is a matter of chain rule. So I just wrote here y is equal to cosecant x squared on the outside, just to make it clear with my chain rule that, oh, I didn't do the working out. The idea is that if I say u is equal to cosecant x, and then y is equal to u squared, then dy du will equal 2u, and du dx will equal minus cot x cosecant x. And then if you multiply dy du by du dx, you'll get this result. So that's how we got here. And then if we can simplify just like so to produce minus 2 cot x cosecant squared x, just like so. Perfect. Looking at question 4, so I added some exponentials here just to mix things up. So the first thing to recognize is, again, if we have cos squared x plus sine squared x equals 1, we can write 1 minus cos squared x is equal to sine squared x. And we have 1 minus cos squared 2x, so we can write, instead of 1 minus cos squared 2x, sine squared 2x. So just being very careful to write 2x, making sure we don't just write x. And then we have sine 2x on the numerator, sine squared 2x on the denominator. We can simplify that just like so. And then here, there's 2 different approaches. This is kind of where I say you, like with trig, you can do, even with the previous questions, there's definitely more than one way of doing it. But I'm just going to go through the working out, treating it with quotient rule, treating it as this, where I have e to the 2x cubed over sine 2x, and treating it like this, y is equal to e to the power of 2x cubed times cosecant 2x, which will produce the same result, but just in a different way. So just starting off here, we can use quotient rule and say u is equal to e to the 2x cubed, u prime is equal to 6x squared e to the 2x cubed, v is equal to sine 2x, v prime is equal to cos 2x, just like so. And then applying the formula, you get this. And you can factor out or something, but I mean, this is a valid answer, so that's good to go. And then using e to the 2x cubed cosecant 2x, you can use product rule instead. Y is equal to uv, where we say u is equal to e to the 2x cubed, u prime is equal to 6x squared e to the 2x cubed, v is equal to cosecant 2x, and v prime is equal to minus 2 cot 2x cosecant 2x. Just remembering to transfer 2x's. Again, if this is a jump, you can always use chain rule with w is equal to 2x. And I've not explained this, but this is kind of covered in my video on differentiating exponentials, so I'm just assuming this is known. And then if you just sub everything into the formula, you get this result, which you can write just like so. And if you do rearrange it, you'll get the same answer as what we did previously, but just one has sine squared x on the denominator and the other does not. Perfect. Final question, question 5. Again, using exponentials, just to mix things up. So this is, we can use chain rule. If we say u is equal to 2 sine 3x plus cot x, y is equal to e to the u, du dx is equal to minus 6 cos 3x minus cosecant squared x. Again, if you want to use chain rule, w is equal to 3x will get you there. Dy du is equal to e to the u. Multiplying them out, you get 6 cos 3x minus cosecant squared x e to the u. And then I seem to have just copied it over. Then if you sub out for u 2 sine 3x plus cot x, because we want our answers in terms of x, you get this expression, and that is question 5 done. So there you go. So that's differentiating trig with exponentials and in a bunch of different forms. So I hope that was some good practice and you feel more confident now. And cool. And that's all I have for you guys today. So thank you for watching. Do feel free to leave feedback. This is the first video where I've realized I don't. I'm aware that it's very easy for me to have skipped some working out or to have overdone it. So please do tell me if you feel like I'm being too back to basics at times, or just jumping around a bit ambiguously. So that's why that's there. Cool. Otherwise, I really hope you enjoyed the video. I hope you have an amazing day.